Have you ever wondered why you don't just float off into space? Or why when you jump you always come back down? The answer is a powerful, invisible force called gravity. It's the ultimate cosmic glue, the silent partner in everything we do. It's a fundamental force that shapes our world and the universe. It keeps our feet firmly planted on the ground. It holds the moon in orbit around the Earth. It keeps the Earth circling the sun. Without gravity, planets, solar systems, and galaxies wouldn't exist. It's the ultimate cosmic organizer, and it's working on you right now. Every single object in the universe is pulling on every other object. You are pulling on this screen. This screen is pulling on you. The chair you're sitting on is pulling on you. You're pulling right back. Even a distant star, millions of light years away, exerts a tiny tug on you. Gravity is always on, always active, connecting everything. Our story begins with a man who was, to put it simply, a science rock star, Sir Isaac Newton. Living in the 17th century, Newton was an incredibly curious and brilliant thinker who asked big questions about the world around him. He wasn't just content with knowing that things happened, he wanted to know why they happened. He developed calculus, made breakthroughs in optics, and formulated the 3 laws of motion. Newton had a knack for seeing the hidden rules that governed the universe, and his biggest discovery would change the way we see everything, from the smallest pebble to the largest star. He was about to connect the heavens and the earth with a single elegant idea. The legend, which you've probably heard, involves Newton sitting under an apple tree. As the story goes, he was pondering the mysteries of the universe when an apple fell from a branch and bonked him on the head, or at least landed nearby. Now, whether the apple actually hit him is part of the myth, but the falling apple was definitely the spark. People had seen things fall for thousands of years, but Newton asked a different kind of question. He wondered if the same force that pulled the apple to the ground. So, what exactly was this grand law that Newton figured out? He called it the law of universal gravitation, and it's beautifully simple. It states that every particle of matter in the universe attracts every other particle with a force. This force is what we call gravity. It's not just a one-way street where the Earth pulls on the apple also pulls on the Earth. Of course, because the Earth is so much more massive, the apple's pull is completely unnoticeable, but it's there. This mutual attraction is happening everywhere, all the time. Your dog is gravitationally attracted to your cat. Your house is attracted to the car in the driveway. You are attracted to the planet Jupiter. Let's break it down with a simple visual. Imagine you and a friend on giant skateboards on a smooth, endless ice rink. If you throw a heavy ball to your friend, the act of throwing it pushes you backward slightly. When your friend catches it, they get pushed backward too. Now imagine you're connected by a giant, invisible rubber band. As you drift apart, the rubber band pulls you back together. For those who like to see how science works in its purest form, Newton boiled his entire law down into one elegant mathematical equation. Don't worry, we'll take it slow. The formula looks like this. F equals g times the product of m1 and m2 divided by r squared. F equals g times the product of m1 and m2 m1. m2 divided by r squared. It might look a little intimidating at first, but each part tells a simple story about how gravity behaves. The F on the left side stands for the gravitational force. That's the pull we're trying to calculate. It's the strength of that invisible rubber band connecting 2 objects. The goal of the entire equation is to figure out just how strong that pull is, whether it's between you and the Earth or between 2 distant stars. On the other side of the equation, we have the ingredients that determine the force. The m1 and m2 are the masses of the 2 objects. Remember, mass is the amount of stuff in an object. So m1 could be the mass of the sun and m2 could be the mass of the Earth. The formula tells us to multiply these 2 masses together. This makes perfect sense. The more massive the objects, the stronger the pull. Next up is the r at the bottom of the formula, which stands for the distance between the centers of the 2 objects. Let's dive deeper into the concept of mass, because it's one of the 2 superstars in the gravity show. Mass isn't the same thing as weight. Your mass is a measure of the amount of matter, atoms, molecules. This amount stays the same whether you're on Earth, on the moon, floating in deep space. Weight, on the other hand, is the force of gravity pulling on your mass. So on the moon, where gravity is about 1/6 as strong as on Earth, you would weigh only 1/6 of what you do here, but your mass would be exactly the same. You'd still be made of the same amount of stuff. Now, according to Newton's law, every bit of that stuff exerts a gravitational pull. The more mass an object has, the more gravitational influence it wields. The second superstar in the gravity equation is distance. While mass determines the potential strength of an object's gravitational pull, distance determines how much of that pull is actually felt by another object. As we've discussed, gravity follows an inverse square law. Its strength drops off very quickly as you move away. Imagine you're standing next to a giant bonfire on a cold night. When you're close, you feel its heat intensely. Take a few steps back. The warmth diminishes. Let's visualize the inverse square law. Spray from 1 inch, a small thick dot. Spray from 2 inches. It spreads wider. That area is 4 times bigger, so the paint is 4 times thinner. Spray from 3 inches. It spreads 9 times more, 9 times thinner. The force of gravity spreads out from an object in all directions, just like that paint. The further away you are, the more spread out and diluted the force becomes. This relationship is crucial for understanding the orbits of planets. Mercury, closest to the Sun, feels a very strong pull. It must move extremely fast, completes an orbit in 88 Earth days. Neptune is about 30 times farther than Earth. There, the Sun's pull is much weaker, roughly 900 times weaker than at Earth, so Neptune moves much slower, about 165 years per orbit. Newton's law isn't just a theory. We see its effects everywhere, every day. The most obvious example is the one that started it all, the falling apple. When an apple detaches from its stem, there is no longer a force holding it up. The only significant force acting on it is the Earth's gravity, which pulls it directly toward the planet's center of mass. Gravity also creates tides by pulling different parts of the Earth and its oceans with slightly different strengths. The moon's pull stretches the oceans, creating high and low tides. From pouring a glass of water to spacecraft orbits, gravity is the underlying principle. It governs everything from tiny droplets to orbital mechanics. Let's take a journey and explore this amazing force. We'll see how a brilliant mind unraveled its secrets. Consider this your official invitation to the gravity party. From everyday falls to cosmic motion, gravity is the rulebook. Next, Einstein gives us a new perspective. For over 200 years, Newton's law of universal gravitation was the final word on the matter. It worked beautifully, predicting the motions of planets with incredible accuracy. But in the early 20th century, another science superstar came along and told us there was more to the story. Einstein's theory of general relativity didn't prove Newton wrong. Instead, it provided a deeper, more accurate explanation for what gravity actually is. He proposed that gravity isn't a force pulling things across space. Imagine a flat, stretchy rubber sheet. This sheet represents space-time, 3 dimensions of space and 1 of time. Now, if you place a heavy bowling ball in the middle of this sheet, what happens? It creates a deep dent, a curve in the fabric. Now, if you roll a small marble near the bowling ball, it won't travel in a straight line. Instead, it will follow the curve in the rubber sheet created by the bowling ball, spiraling inward. This is Einstein's vision of an orbit. One famous example is the orbit of Mercury. Newton's law couldn't fully account for this wobble, but when astronomers applied the mathematics of general relativity, the prediction matched the observations perfectly. Einstein's theory also predicted that gravity could bend light. This was confirmed during a solar eclipse in 1919. From a falling apple to the fabric of space-time, our understanding of gravity has come a long way. We began with the intuitive feeling that something holds us to the ground, and through the genius of Newton, we learned that this something was a universal force connecting every object in the cosmos. His simple law, based on mass and distance, gave us the power to chart the heavens and understand the clockwork of our solar system. It showed us that the rules governing our world are the same rules that govern the most distant stars. Gravity, we learned, is the great equalizer, the force that binds the universe together on every scale imaginable. Then, Einstein took us a step further, revealing a universe even more wondrous and strange than we had imagined. He showed us that gravity is not a pull, but a push from the shape of space-time itself, a deep and fundamental connection between matter, space, and time. This new perspective allowed us to understand the most extreme cosmic phenomena, bending of starlight and black holes. But for everyday calculations, Newton remains a fantastic approximation. Without its precise strength, the universe would be a vastly different place. If gravity were slightly weaker, stars and galaxies might never have formed. Gravity's perfect tuning allowed for the formation of our sun, our planet, and the stable environment needed for life to emerge. It holds our precious atmosphere around us, gives us the water we drink and the air we breathe, and connects you, me, and everything we can see to the grand, beautiful cosmos.